Hello and welcome to Chapter 9. This is going to be the Sun. We're going to talk about our favorite sun, which is a very ordinary star, and that thing is supposed to be moving. It kind of gives you the idea of a tropical sequence here on the planet. Low sun in our atmosphere looking kind of reddish orangish, and the waves actually pulling off some really beautiful reflections. But in reality, the sun is not this tranquil tropical paradise producing star. It is a very violent, dynamic monster. Luckily, it's 93 million miles away, and we don't have too many references to this material. If you were up in space station, they do have to worry about some of this stuff, like the solar wind, the high energy waves that do come out. We'll talk a little bit about that in Chapter 9 as well. Okay, so what are we going to do? And those little loops of gas you saw on that last screen, they can be bigger than the Earth. These are called prominents, and they really are. They're very prominent. Okay, so here's one showing you a very dynamic solar surface as well. How does the mass of the Sun compare to that of the rest of the solar system? Are there any stars nearer to the Earth than the Sun? Does the Sun have a solid and liquid interior like we do here on Earth? How does the surface of the Sun appear to us? And does the Sun rotate? And lastly, what makes the Sun shine? Okay, so 9A, and this is, I'm going to watch it. We're about 1:45 seconds in. I'm going to watch that, and when it gets to 15, I'm going to stop it, and I'll make that B. If I get through the whole thing, that's great, too. Okay, by far, most of the solar system's mass is in the Sun, somewhere between 99.8 and 99.9. And if you look at this blue circle, that is the Sun. And if you can make out a little color here, it looks like it's kind of reddish. That's because that's Jupiter, very small percent, and you may be able to make a little green next to it, which is Saturn. And of course, there's Uranus and Neptune, and then all the terrestrial planets in there as well, but they are so small at this scale you can't even see them. Okay, here are the vital statistics. I would like you to know its mass in terms of, actually probably don't need to know its mass other than 99.85% of the solar system, but it's 3.3 times 10 to the fifth, so it's 333,000 Earth masses. That's a bunch of Earths. I do want you to know the radius. 109 Earth radius, so if you go from one side to the other, top to bottom, anywhere in between here, you're actually going to take 109 Earths to make this. Maybe you can hear my wife sneezing in the background. Luminosity, it's in watts, and that's 10 to the 26th, which is just monster wattage. A lot of energy, a lot of light. I would like you also to know its mean angular distance, 32 arc minutes. And how we figure out arc minutes, you take degrees, like on a protractor, take one of those degrees and zoom it out, so we actually get 60 what are called arc minutes, and this is 32 of those, so it would be basically this big, and then we can go to arc seconds and actually see that too. So what does that mean? 1 degree of arc is the little finger held out at arm's length, and this is 1/2 of it. So that's 60 arc minutes. This is 32 arc minutes, so it's half of that. So you can cover up basically two suns sitting next to each other with your little finger at arm's length. Pretty amazing. Is there anything else I wanted you to get on that? Mean distance, understand that it's, we do get farther away and closer to it when we talk about perihelion and aphelion. Mean distance, I would like you to know that light traveling to the Earth, about 8.5 minutes. Surface temperature, we'll talk about those later on. Its composition is 74% hydrogen and 25% helium with a whole bunch of other elements. Remember, we found the elements in the periodic chart on the Sun. Composed by a number of atoms. Looks like the number of atoms, because these are not quite as massive, it's mostly still hydrogen. Distance from the center of the galaxy, we don't need to know. Orbital period, we don't really need to know. And orbital speed, we don't really need to know, although understand that it moves very quickly. That's a lot of kilometers per second. Okay, here's the Sun under a whole bunch of different colors. these are wavelengths, and you can see there's a normal sun, and then there's a green, normal sun and a green, and then a light blue, and we'll talk a little bit more of these when we actually get to a web quest that we're going to do. But you can actually see that they're showing you lots of different, showing you 3 sections of the same material, but really beautiful sun. And what they're doing is they're actually looking at it through different filters, through telescopes, and they allow different wavelengths of light to go through, and that of course shows you different materials. So if you take a look at the sun, you can see a little bit more definition there. Maybe able to make a little bit more definition, but it's the same sun looking at lots of different wavelengths, and you can show, some of them show the atmosphere better, some of them show the sunspots, and you can pretty much only see one, maybe a couple sunspots here, but you can see there are a lot more material that it's actually visible with other types of light. Our sun's neighborhood, if you take a look at the sun is in the center of this circle, and it goes out to about 4 light years, so 1, 2, 3, 4 light years. And if you take a look at, this doesn't really show you where these things are located, but Alpha Centauri, actually Proxima Centauri, which is part of the Alpha Centauri binary, trinary, is actually the closest star to the Earth. You can see it a little better here because now it's got the sun. It actually shows you where these stars are located, but then it also shows you in terms of distance. So Alpha Centauri, which they're saying is right here, is less than 1 parsec, which is actually 26 light years away. So it's actually sitting out here about 4.3 light years away from the Earth. I do want you to draw this picture. This is a cutaway version of the sun. It actually shows you the thermonuclear core. This is where this hydrogen is being fused into helium, producing a bunch of energy. I do want you to know the radiative zone, where it actually radiates. This is sort of like when you put your hand out to a campfire. You can feel the radiation, and then it's got a convective zone, which actually moves the energy from the core through the radiative into the convection out to the surface, which is called the photosphere. So this is the interior's 3 layers of Earth, of the sun, as well as the photosphere. The atmosphere of the sun has 3 layers. I'd like you to draw this as well. So we have the photosphere sitting on top of the interior of the sun, and then we have a pinkish colored chromosphere. This is why it's called chromo, which is colored sphere, because it has this pinkish alpha colorish to it, which goes up into very small pointed shapes, which I'll show you later on, called spicules. And then sitting on top of that is the corona, the crown layer of the sun. So the 3 layers of the atmosphere, they're saying, is the photosphere, which is sort of the surface of the sun, as well as chromosphere and corona. And I do want you to draw that. And you can see 0 elevation up to about 2,000 kilometers, 4,000 kilometers, 6,000. This can be 8,000 kilometers, 0.6. That's almost 5,000 miles tall. Really tall spikes. And these are going to be called small sections because the prominence are going to be a lot larger than this. Okay, so we got the photosphere sitting at the surface of the sun. We have the lower chromosphere, the upper chromosphere, and the corona. And you can see 6,000 degrees Celsius. That is the temperature of our sun when we actually talk about, oh, be a fine boy, oh, be a fine guy, kiss me. We're a G star, and we're about 6,000 degrees Celsius surface temperature. It actually cools as we go up, and then it heats up to 1 million degrees for the corona, the crown layer. And the crown layer, that's the layer you draw with when you draw the sun. You draw those little lines coming out. That's really the corona that you're drawing. So layers of the sun, 9 minutes in. Sun's interior, it's made of the core, and this is where thermonuclear fusion with hydrogen happens, where we take hydrogen and turn it into helium, losing a little bit of mass and producing a bunch of energy. E is equal to mc squared. The radiative zone, this takes the energy produced in the core and carries it out towards the surface by radiation. And remember, we have radiation, conduction, and convection. We don't really have conductive heat in here, but we do have radiative heat, and this is going to be producing photons for light. The convective zone takes the energy from the radiative zone and carries it out toward the surface by convection, and this is as heat. And then we have the sun's atmosphere, the photosphere, Actually, this is the solar surface. The lowest layer emits visible light, and this is what we actually see with our eyes. Chromosphere, the middle layer, this is transparent and allows us to see the photosphere. And the corona, which is the upper layer, also is transparent, which still allows us to see the photosphere, although it does cause a little bit of color change. It's pretty much the same thing. Okay, we're 10 minutes in. So here's a picture of the sun, actually showing the dark areas, which we call spots, sunspots. So the surface of the sun is bright. It's producing visible light. It's very bright, and it's producing from the photosphere because it's producing photons, the visible light that we actually see. It's kind of neat to think about these, but the photons are actually created in the center from the heat of the thermonuclear reaction, and they zig and zag, and it's actually theorized that it takes more than 1,000,000 years for this photon to zig and zag to make it out to the surface, and then 8 minutes and 32 seconds later, another 9 or so minutes to actually reach the Earth. So 1,000,000 years to get out to the surface, and 8 minutes and 32 seconds to get to the Earth. When looking at the sun, the outside produces a little bit of, it actually looks like it produces more orange light, and we're not exactly sure what this is, but we call this the limb, and it's called limb darkening, where we go from yellow a little bit darker toward the red end. It's going to be orange, so we actually see this orange observation of the photosphere, even though it should look bright yellow through our atmosphere and everything. But it's probably just because it's curving away, and we get to see a little bit more light, but most of the light's bouncing away from us or moving away from us and not toward us like it is here at the middle. Remember that the sun is powered with thermonuclear fusion. It is not, and I repeat, it is not on fire. Two cool animations. I like this one because it's throwing out all kinds of material in this prominence, which is an open prominence which goes out. It actually has another prominence here which is not moving out near as quick, and that could actually be a coronal mass ejection or a solar flare. Okay, upon closer inspection, if you look at the surface of the sun, it has this granular kind of appearance, and these things are actually called granulation. And what they basically are is with material at the photosphere that's hotter, moving up toward the center, bringing up brighter, hotter color, and then it actually goes back down to produce this. Here's what it would look like if you could really watch it, and it's very, very, very dynamic, very, very quickly changing. This is not true time. This is actually probably 100 or 1,000 times longer than what you're seeing, but it is very dynamic. It actually happens around sunspots too, where the material is actually going in. Sunspot is dark because it's 1,000 degrees cooler than the photosphere, so 6,000 degrees for the photosphere, it's 5,000 degrees for a sunspot. But you can actually see this is where material is going back down into the sun. Here's another view of a sunspot. You can see the color changes from yellows into oranges into reds and then finally into black as the temperature cools. During a solar eclipse, we actually get to see a total solar eclipse. We sometimes get to actually see this pinkish area around the sun, and this is what's called the chromosphere. It's producing hydrogen type spectra, so it's producing sort of a pinkish type of color. If you take a look, this is the spicule we drew, and it actually shows you it's pink. They're showing you it's pink here too, and you can see it's pink in this alpha, hydrogen alpha filter. Here we're actually seeing a false color. These are both GIFs. Actually, all the animations you're seeing in this presentation are GIFs. But you can see this stuff moving up, and it's like 6,000 miles tall. So they're small little things, but remember the sun is a very large circle. Okay, probably the last thing we're going to talk about is the solar corona. This is the big source of solar wind. It is very visible during a total solar eclipse, and you can see that pinkish area that's around for the chromosphere, as well as the crown layer, the corona. And it's also very easy to see in terms of X-rays, because this actually shows you the 1,000,000 degree gases that are in the corona opening up. And I'm going to call it quits there at 15 minutes. All right, so this will end A and this will begin B. Bye.